Hello viewers, welcome to my second video on soil mechanics. Today I'll speak on Atterberg limits. So first of all, let me give you an overview of soil classifications on the basis of particle size given by different organizations around the world. So here I have tabulated some soil classifications given by different organizations like MIT, United States Department of Agriculture, AASHTO, Unified Soil Classification Systems. All these organizations have classified soil into four categories, that is gravel, sand, silt and clay on the basis of particle size in millimeter. So these are the ranges of particle size given by these organizations to identify the soil types. So here you can see the coarse-grained soils are mainly gravel and sand. These are of larger particle size, and silt and clay are of finer particle size, clay being the finest particle size soil. A graphical presentation of this table is shown here. So let us call these soil separate size limits by various systems, and these are the ranges of particle sizes for different organizations, MIT, USD, AASHTO and USCS. You'll see that there is no big difference in opinion between the organizations regarding the particle size based soil classifications. The only exception you must have noticed here is with Unified Soil Classification System. This classification system does not separate silt and clay. They put any soil particles less than 75 micron or 0.075 millimeter as silt and clay together. But all the other classification systems, MIT, USDA and AASHTO, they separate silt and clay on the basis of particle size. Anything less than 0.002 millimeter is termed to be clay soils by all these three organizations. Now, these are the broad classifications: gravel, sand, silt, and clay. But for our purpose, we also make some subcategories, or we combine this gravel and sand, the larger particle size soils. We call them cohesionless soils. By cohesionless soils, we mean that these types of soils, they flow freely when they are dry, and they don't become sticky when in contact with water. On the other hand, the finer particles like silt and clay, combinedly, these are called cohesive soils. That means these soils exhibit unique characteristics of being powdery when they are dry, and they become sticky when in contact with water. So the properties or the characteristics are kind of opposite to each other for cohesionless soils and cohesive soils. Now we'll describe the terms Atterberg limits, and please note that the Atterberg limits terms are applicable for cohesive soils only. These are not applicable for cohesionless soils. That means these are applicable for silt and clay type of soils. So let us take a mass of soil which is in solid state, that is in oven dried condition. You can get a mass of soil in oven dried in solid state when you dry it in oven for a prolonged period under a certain high temperature, or also this type of soil can be obtained in a drought situation, in a prolonged drought situation, or in a prolonged no rain season situation. Now this is the phase diagram for the soil in its solid state, that is, there is no water. Now if you add some water and gradually increase the amount of water at some point of time, after adding water, say WW1, from solid state, the soil mass will enter into a semi-solid state. So this is the corresponding phase diagram in the semi-solid state. Now if you keep on adding more water, and after adding say delta W1 weight of water to the semi-solid state soil, it will enter into another state, that is the plastic state. By plastic state, we mean that the soil in this state is remoldable. For example, the soil that is required, the consistency of the soil that is required for making sculpture. So if you want to visualize it, you can visualize it that way. So this is the phase diagram in plastic state. The solid particle, the weight of solid particle is obviously scale Ws, and the amount of water in this state is WW2, which is higher than WW1. Now if you add some more water to the soil in its plastic state, and after adding say delta W2 amount of water to this state, it will enter into a state that is called liquid state. That means in this state, the soil will start flowing on its own weight. Okay, that means it will become liquidy. It will have very little resistance against any load or force. So this is the corresponding phase diagram in the liquid state. As you can see here, this is the solid particle, the weight of the solid particle, and this is the weight of water. Obviously the weight of water in this state is more than this, and in this state is more than this, and in this state is obviously more than the solid state weight. Now we can define the Atterberg limits. In fact, there are three Atterberg limits. One is called shrinkage limit, the second one is called the plastic limit, and the third one is called the liquid limit. The shrinkage, all these limits are actually water content at different states. Okay, so the shrinkage limit is the water content or the threshold value of the water content that transforms a solid mass, soil mass, from its solid state to the semi-solid state. So that is the shrinkage limit, and this can be obtained as water content which is WW1 to WWS, right? Next Atterberg limit is the plastic limit, that is the threshold value of the water content that transforms the soil mass from its semi-solid state to the plastic state, and this can be obtained by this. And the liquid limit is the third Atterberg limit, which means the water content, the threshold value of the water content that transforms the soil mass from its plastic state to the liquid state. Okay, so these are the three limits which are combinedly called the Atterberg limits, and all these limits, the shrinkage limit, plastic limit, and liquid limit, all these limits are specific to cohesive soils only. There is no such term for the cohesionless soils. Like for gravel or sand, you never say shrinkage limit, plastic limit, or liquid limit. Okay, and let us now have more inner look, or try to develop some insight into what happens to soil when they are in shrinkage limit, or in plastic limit, or in liquid limit. So when the soil mass is on this boundary line, that is transforming from solid state to semi-solid state, or when the water content in the soil mass is equal to the shrinkage limit, in that case the stress strain behavior can be like this. And because it is transforming from a very hard state, or from the soil skeleton state, to a semi-solid state where there will be some or insignificant amount of water, it will take a lot of load. The soil mass will be able to take a lot of load when it is, or the water content is at shrinkage limit. After adding some more water, that is when the water content will be equal to plastic limit, the load carrying capacity of the same soil will decrease. Okay, and after adding even more water to the soil mass, that is when the soil mass will have water content equal to liquid limit, then it will be able to take very less amount of load or stress. This is something you don't want in your real life. You don't want your the natural water content or the water content of the subsoil to be closer to liquid limit, you would like to, obviously you would like to have it close to the shrinkage limit, but shrinkage limit means a very dry state of soil, almost skeleton state of soil. So this really doesn't exist in real life. In most of the cases, for all our practical purposes, the water content in soil varies between plastic limit and liquid limit. We'll talk more about it later on. So these Atterberg limits actually give you kind of an indication about the relative strength of the soil you are going to deal with. Right. Okay. Let us have a look at it in a different way now. So, our in all real life situations, the water content in cohesive soils will range between the plastic limit and the liquid limit. That is what I said just a moment ago. And now, if the natural water content, that is the in situ water content, that means if you collect the soil from underneath the ground and determine its natural water content, if the natural water content is close to plastic limit, as you can see here, as I have put here, if this is close to plastic limit, that means your soil is going to exhibit high strength and it is a competent soil for your foundation. Okay, and if the natural water content of the soil is close to liquid limit, that means if it is far apart from the plastic limit and very close to liquid limit, that means it is on the verge of flowing under its own weight. That is the definition of liquid limit. Okay, so that means at this stage, your soil is gonna show very low strength. Okay, and you may consider it to be incompetent. So just by determining the liquid limit and plastic limit of a soil, which are intrinsic properties of your soil, and also by determining the natural water content of the subsoil you are going to make your structure on, you can easily put it on the scale and see if it is close to plastic limit or if it is close to liquid limit. If it is close to plastic limit, you must be happy. If it is close to liquid limit, you should not be happy. Okay, and this actually gives you a very quick understanding of the property or the capacity of your soil. Now we can have another definition. We can have a definition like liquidity index, and liquidity index is called natural water content minus the plastic limit divided by liquid limit and the plastic limit. Okay, so if liquidity index is 0, when the liquidity index will be 0, when the natural water content will be equal to plastic limit. So at plastic limit, the liquidity index of your soil will be 0, and at the liquid limit, the liquidity index of your soil will be 1. That means if the natural water content of your soil is close to liquidity index 0, then it is a high strength soil and it is good for your foundation. And if it is close to liquidity index 1, it is a poor soil. It will exhibit low shear strength, low resistance, and you should not build your structure on this type of soil, without any treatment. Okay. Right, we have another definition, and it is a very important definition as well, and this is called the plasticity index. Plasticity index means the difference between the liquid limit and the plastic limit. Okay, plasticity index is the difference between the liquid limit and plastic limit. If we go back to our previous slide, the difference between the liquid limit and the plastic limit is called the plasticity index. And on the basis of plasticity index, Burmeister has classified cohesive soils in different consistency. For example, if plasticity index is 0, when the plasticity index will be 0? Plasticity index will be 0 when the liquid limit and plastic limit will be the same. Okay, that means it will have no plasticity. If the plasticity index is 0, that means the liquid limit and plastic limit will be 0. That means it will have no plasticity, non-plastic soil. And actually the gravel and sand, that is the cohesionless soils, they will always exhibit plasticity index equal to 0. And there are other ranges like 1 to 5, 5 to 10, slightly plastic and low plasticity soils. These are actually the silty type of soils. So whenever you get a plasticity index after carrying out the laboratory tests, determine your liquid limit and the plastic limit. I'm not going to show you all those laboratory tests here. If the value of plasticity index of your soil after testing, if you find that the value is equal to 10, you should be able to understand that this is probably a silty type of soil and not a clay type of soil. For clay type of soils, the plasticity index will be more than 10, 10 to 20, 20 to 40, and even higher. So these are all different types of clay soils of different consistency, that is medium plasticity, high and very high plasticity. Okay, so the plasticity index gives you an idea about the type of soil as well. And to be more precise, if you want to use the plasticity index to identify your clay type of soil, remember that plasticity index all the Atterberg limits, these are all related to cohesive soils only. You are not going to find anything related to cohesionless soils when you are talking about Atterberg limits. So this is a plasticity chart. You will find it in ASTM as well. I'm not going to explain much about it. You'll find it in any book of soil mechanics and also in your other lectures. So this plasticity index can be used to determine the types of soils of different plasticity using this plasticity chart. Okay, there is one line called A line, which is given by this equation. There is other line called U line, which is given by this equation. And on the x-axis you have liquid limit. And on the basis of the value of plasticity index and liquid limit, you'll have to see in which zone your soil falls. And on the basis of that, you can easily identify the type of your soil. For example, if the plasticity index and liquid limit suggest that your value is this one, in that case, your soil will be a high plasticity clay or high plasticity organic soil. Okay, so this is another use of Atterberg limits and the plasticity index. Now, let us try to understand the plasticity index from another point of view. So as I said or explained already, that plasticity index is the difference between the plastic limit and the liquid limit. High plasticity index also means that for transforming the soil from the plastic state to the liquid state, you'll need a lot of water to add to the soil. Okay, that means these types of soils which require a lot of water to be added for being transformed from plastic state to liquid state, these are less vulnerable to erosion, and these are less susceptible to change in moisture content. So wherever you have wherever you need soils which should be less vulnerable. For example, if you have a mountain which is clay predominant, in which the soil particles are mostly clay and less sand, then under a rainfall during monsoon, it will be less vulnerable to erosion. Okay. Similarly, if your river bank is composed mainly of clay particles, it will be less vulnerable to erosion. right? But in Bangladesh, unfortunately, most of the hills and mountains and also the most of the river banks are soils having low plasticity index. That means these soils are either silt or sand or a combination of silt and sand. That is why our river banks are always more vulnerable to erosion and our hills are more vulnerable to landslide. Okay. I hope you found it interesting, and I'll come back with more videos on soil mechanics. Step by step, we'll get into the design part of our foundations for buildings, for embankments, and for many other structures. Thank you very much. Thanks for watching.